This is the presentation for my Python assignment. So I started looking at the problem, and this is on the left hand side. It's my early work. As you can I see, I try to solve it as one single tile block with a distance of zero point 0.5 meters, and and I didn't divide up into smaller section. And I used in time formula. I didn't set the stability criteria to be one half. Thus, I have the wrong answer. I got around 45 hours, which was way off. So I had to go back and rethink the problem. And so when I look at the problem again, I divide it down the middle. You can see on the right hand side that I divide into two sections, left and half, with 0.25 meters on each side into two block. And then I set the stability criteria to be zero point 0.5, which will eliminate the third term, which leaving me with TC with this equa equation right here, which is easier to work with. And then I solve for the time manually, which got me to be around 15.25 hours, which I think was close, but it was kind of far off. So I went to the Python and I coded into the Python. And first, when I coded to the Python, I realized that my time was started 0 degree T temperature, and so I had to add it at 300 degrees to make it the starting temperature of 300 degrees Celsius. And I set my A is equal to my alpha value, the T equal to 0 because that's just at time 0. Um, and no, dt is time 0. X is the distance I divide into half, so of 25, 0.25 meters each size. And the Tc is the temperature that I'm looking for, um, which is the temperature in the middle of the center, which is basically 425 degrees Kelvin. So to do this, I have to create a while loop to create the data as it go over time. And so at so I want to set it up so that way it will stop when TC reaches 425. Because that's the temperature inside of the in the middle. And so I set up dt to be equal to 0 because start at time 0. Then it will add 1 second every time the loop go through it to increase it. And I mentioned that I realized that at the beginning, since it started at 0, the temperature will be 0, and so I had to add 300 degree after that to make it start at 300 degree Celsius Kelvin, because that is the temperature that it started at. And then I created data for to capture the time and temperature data. Time is the x-axis and temperature is the y-axis. So it captures data every time I go through the loop and save it for future. Then I plotted the time and y. And so time on the x-axis and temperature on the y-axis. Then the type is a line graph, and and to show the and to show the plot. Also, because since time is in second and I want it in hours, I just have to divide it by 3,600 to get to change for a second into hours. Then I print out the time, the text, the plot, and the temperature in T, because T is the time and dt is just the time in second. T is time in hours. So I got 17.5 hours is the answer. And then here I've answered part C of the system. And this right here is the graph that I have. It's a linear graph. It's just a straight line. So you can see that it's in second, and and I think I kind of expect it to be a line graph because it linearly increases over 1 second every single time. And this is the problem that I choose for my um, problem for the textbook that I choose. I choose question 2 dash 67 of the sixth edition of the textbooks. So this question asks me what is the temperature on the inner surface of the furnace. Well, in order to do that, I must use conduct the law of conduction. But in order to do law of conduction, I need the temperature on the outer surface of the furnace. In order to calculate that, I use the relationship of heat flux times H, this equation at the top, to solve for the temperature on the outer surface of the furnace. And since, as you can see, the surface raised to the fourth power on on this terms, and first power on the first term, I can't isolate that to solve it. So I use a calculator to solve for the surface temperature on the outer surface, which I got to be 592.4 degrees Kelvin on the outer surface of the furnace. Then I use Fourier law conduction, isolate transfer into dt dx equal to negative q over y. I have integrated that, and I got t is equal to negative q k plus c. Then rearrange that equation, and I got the temperature on the inner surface equal to Q my over K times the length, the thickness of the thickness of the furnace plus the temperature on the outer surface of the outer surface of the furnace, and then I got 596.4 degrees Kelvin. And so for this one, I did the same loop as I did with the problem number one because I can't isolate the t because it's raised to the fourth power, fourth term in t. And so in order to solve for this, I have to like do the loop that go up by zero point 0.1 to make it more accurate, because if I go by 1, then it's not as accurate because it will skip over the right answer. I have to go by 0.01 to make it still smaller to give it a more accurate answer using this method. And so and then once I solve for the outer surface temperature, I will plug it into the equation I developed to solve for the inner temperature of the surface. And this is the code for it right here.